Okay, here we are. Doug and I are going to do a trial run of the video recording. Doug, go ahead and introduce yourself, please.
Okay, my name is Doug Reichman. I work here in the media studio, and I'm just excited for this project.
Me too. All right, so I went ahead and I wanted to be the guinea pig on this, so I wrote a few questions for Doug to go through. So go ahead, sir. We'll kind of test these out, see what we think.
Okay, please tell us where you are from and when you will graduate from SWASU.
Okay, so we wrote these questions for the students. I'm originally from Northwest Kansas, which is not terribly different from Western Oklahoma. And I graduated with my bachelor's degree in 2003. So it's been a while. I actually graduated from Kansas State University, a state university not a whole lot different than SWASU.
Okay. And tell us what your project is.
So the one that I'm really excited about is what they refer to as the traveling salesman problem. And this is a classic computer science problem. It's considered an open problem, meaning people don't have a fixed solution to it. The problem itself is, if I give you a list of cities and the distances between all the cities, can you tell me the fastest path to get through all the cities if you only get a pass through each city once? And we've got a simplified version of that. Instead of having GPS coordinates, what they did for this is it's just a list of distances. And so our job is working through this matrix of distances between cities to find the fastest path. The algorithm that our team is using to find this, find a solution, there's lots of good different ones. We're going to try brute force, which is basically try all the paths and see which one is the fastest. But we're also going to look at the guess and check method, and it's literally, let's randomly choose a path. What's its distance? Is it better than the last distance that we randomly checked? If yes, let's keep it. And if the answer is no, then let's just guess again. And the nice thing about that is it's simple. And because we're working with a cluster of computers, there's not a whole lot of coordination. We just tell all the different components of the computer, just keep guessing until you find one that you like, or find one that's faster, and then keep guessing and you might find another one that's faster. The third algorithm that we're going to try, the third part of the problem, is we refer to it as ant colony optimization. And this is something that some folks came up with in the 90s, and it was the observation that ants are really efficient. They're really smart, really strong, and they do a really good job of finding very efficient paths to get from where the food is back to their home. And so they started to think about, wow, how could we capture this efficiency for path planning? Could we do this in a way that we could write a computer algorithm? And I wonder if that computer algorithm would help us solve these more complicated problems. And what the researchers suggested is this is actually a really good way to do this. So the task that we have, currently we have a version of the ant colony optimization. We've got it written here in Java, and it basically, it's based off of the 1996 paper, ant colony optimization, and it runs in Java. It runs on a single thread, and it runs in Java, and it's a little bit slow. But this could work. We could feed it the source code that or the source file that they're going to use at the competition, and we could use this to be competitive. Now, we've kind of worked through the notes, and Adam Fuller is actually the one that latched on to ant colony optimization, and we went and we started to lay out what we were going to need to do for the project. Now, the first thing that we're going to need to do is convert it to C code. And we're all big C groupies as it is. We're really excited about C programming just because it's cool, it's sexy, people have heard of it and they like it. There are a lot of newer languages, there are different languages, but for doing things in a high performance computing environment, Fortran and C are actually still the big languages. So what we want to do is we want to work through taking the code that we have in Java, getting it over into C, and then we're going to add in a few different things. Basically different jargon or different little keys inside of our code that allow us to do things like, if we've got a processor that has more than just one core, how can we get all of the cores to participate in the work. And then if we've got a computer that's actually a computer system made up of multiple computers networked together, what can we do to make those computers talk to each other efficiently? And the way that we plan on to doing that is a little further down here. There's this program called Message Passing Interface, or MPI, and that's something we're still working through.
Very good. What interests you about your project?
I love to make things go fast. All of my life, I've loved to make things go fast. And probably my favorite thing about making software go fast is the cost. It only takes your time, and you can run your software as fast and as hard as you want. And if you blow your software up, luckily we've got tools that we can literally rebuild the software, go back to right before we blew it up almost instantaneously. So unlike racing drag racers or something like that, it's much cheaper and it's much easier to fix problems.
Very good. How did you get started working on this?
I would love to give kudos to my friend Peter Harlick. He's at the University of Tulsa, and he's their computer science faculty there, and a high-performance computing guy, and has been for a long time. And I've had the pleasure of working with him on several projects. But he hosts the competition, and this year he said, "I'm going to up the bar a little bit." And he added this other programming track, and I'm really excited about it because this is something. The programming track that we had the last 2 years for the high performance computing has been very much how well do you know C programming, and how well can you turn on the tricks and the tweaks to make C programs run faster. And this program is significantly different because it is an open solution, and they're not really, there's not one set way that makes this work, and it really is what's the most efficient software that we can come up with to solve this problem. And it's not simply how fast can we use different libraries to solve the problem. So like I said, Peter Harlick, that's really the guy that's making this happen, that's helping us keep going down this path.
Okay. What has been the most exciting things that you have done so far with the project?
For me, the most exciting thing really has been seeing the students slow down and start to do things like learn what C programming is, learn how to do a Google search for an academic paper, and then how to interpret that paper and translate it into actual code. And taking the time to think about things and learn how to do things that they wouldn't necessarily normally do for a homework assignment. And probably the best part of that for me is, because this is hard, we're actually seeing students starting to interact more with each other and build a stronger community. And for me, that's the experience, especially the friendship of the students. That's been the best part.
Okay. What have been the biggest challenges so far?
Time. Honestly, the number one thing that we run into with a lot of our students is we don't have enough time to get everything done. And so specifically what I mean is I would love to have an extra 20 hours a week of one of my students that they could just get involved with a project like this and keep the ball running. I swear I have the smartest students in the world, the best students in the world. And if I didn't have to do things like split my students with Walmart and Subway and Little Caesars and Pizza Hut, and I've got some that work here in the library doing editing, I think we'd be a lot further down the path. But as it is, we just don't have the scholarship money to match the dollars per hour that the other companies in town can, and therefore we lose out the time on our students. And so the number one thing that I hope to solve through promoting our students' work, trying to get students to get scholarship activities or scholarship funding and things like that, I really hope to just get more time, because I feel like when we can solve that issue, I think we're going to really start to see the student projects take off and really start to see the full capability of the students that we have.
What parts of the projects have required the most work and attention so far?
The time management and keeping all the team on the same page. When we're balancing we've got 4 members per each team, and each team also has a faculty advisor, and getting a time where everybody can sit down together and work together, that really has been the most difficult thing. And what we've actually come up with is normally we meet on Fridays from 3 to 5. The problem with that is if we ever have other meetings that overlap with that, or like this week, we've got the Oklahoma Research Day on Friday. So even when we pick a very strange time when everybody else is trying to run off of campus to have meetings, it never fails that we still have things that'll pile up on top of us. And so getting people together really is the most difficult thing.
Okay. What are the big things coming up for your project in the next 3 weeks?
Spring break. And the reason why that's exciting, hopefully we're going to be able to, we're refactoring the code right now, getting it from Java into C. And I'm hopeful that during spring break, our team will have a few more hours where we're not dealing with regular homework. And then we can turn on things like the additional libraries to let more of the computers get involved with the project, like OpenMP and MPI. So that really is, we're optimistic. And the thing that I'll say that will for sure get done within the next 3 weeks, I'm excited to say we will have a C program that'll run in the next 3 weeks.
That's great.
I'll make that commitment. It's my goal. I understand a lot of things can go wrong to keep that from happening. Life happens. But I'm really optimistic that's what our team can do in the next 3 weeks.
Okay. Do you have any fun stories related to your project?
I think the most fun that we've had was the first day that the team really started to get involved with ant colony optimization. And we were trying to explain pheromones, right? And we've got a room full of computer scientists, and they understand things like C code and for loops, making a variable. But we had a biology student that had a major in biology, and they were trying to explain this. And finally he took a step back and he's like, stink. Pheromone means stink. And we're like, oh. And he's like, no, what you need to understand is the ants that travel faster, how they model that is, if your path is shorter, that means you're effectively traveling faster. And if you're traveling faster, you're going to have less of your stink or your pheromone evaporate off. And so that'll leave a stronger trail. And so that's when we started to call it the stink matrix. And it's fun to see these students that have been steeped in academia for almost all of their lives to take a step back and just kind of figure out, how can I explain this in simple terms that everybody can understand? And this was a great example of our student was able to just nail it on the head, find a way that they could explain the problem in a way that everybody else could latch onto. Since then, we've had great success. That was the kind of the watershed moment where we really started to get traction. We went home. One of the team members wrote the Java code to do ant colony optimization in Java. We were able to show that it worked, and it was actually rather efficient. And so since then, everything else is kind of built off of that moment where the one student figured out, don't call it pheromones, call it stink.
What are your big project goals by the end of the semester?
We want to win. We want to win and be successful at the Tulsa competition. We've got, there are really two different programming tracks. One is a mathematical problem that really comes down to how well do you know the C programming libraries. Then the other project, this one that I'm much more excited about this year, getting the students started on, which is the ant colony or the traveling salesman problem. The goal for both of those, though, is we want to go to Tulsa and we want to show, we want to do well. Last year, we finished first place in the undergraduate competition. So third place was third and second. One had about a time of 1 hour and 6 minutes. The other had a time of about 56 minutes. And then our team was able to, this was a race, how quickly can you get it done? Our team completed the project in 6 minutes and 45 seconds.
Oh my gosh.
And so we took first place, handily took first place. Yeah. And our goal is to go back again this year and do well.
Sounds like you have some big shoes to fill.
We have a lot of fun. Yeah. It's some of the team that was actually able to make that code work last year is still on the team this year. So we're excited. We're optimistic.
You got your work cut out for you.
Absolutely.
What advice would you give to others getting started on your project or on similar big projects?
The one thing that I would say is don't spend any money. The last thing you should do is start spending money. The first thing that you should do is get a hold of the problem that you're most interested in. You know, we're doing the two problems: ant colony optimization, or traveling salesman, and finding the determinant of a large matrix. If those problems aren't interesting, find one that is. But as soon as you find that problem that's interesting, sink your teeth into it. Do a good job of taking notes. What's what worked, that's important to know, but the other thing to know is what didn't work. And if you do find something that does work, or if you find a way to search for how to fix what doesn't work, take notes on that, and just kind of make sure that you're setting goals for yourself, but make sure that those goals go back to something that you're interested in. It's easy to find somebody that is completely capable of doing the programming, but if you get hung up on a project that you're not willing to work on, if you're not interested in it, you're not going to be very successful. But if you can find something that you're passionate about and then work on that, and really work at it hard in a disciplined, well-documented way, I think whatever it is that you try to take on, you're going to be successful.
Okay. What do you plan on doing after SWOSU?
Um, I plan to die here. That is actually a personal goal of mine. I literally can't see myself ever doing anything but teaching at SWOSU.
All right. Thank you for being with us today.
Doug, thank you. This was a great pleasure.